Okay, welcome back to video 2. I've just managed to upload video 1, so here we go. This is a little recap. So when you've got a metal aqua ion with its 6 water ligands, this is acidic, and it's acidic because this metal ion is pulling electron density towards itself, so these hydrogen ions can drop off. Now in the presence of a base, like a strong base like hydroxide, so what happens here is the hydroxides pluck off these loose hydrogens, and therefore you make, so if I draw over here, this water was still intact, this water was still intact, this water was still intact, sorry, that should be going to the oxygen there. This water will still be intact, this will be OH, this will be OH. And overall you'll have a complex with no charge. So if it was 2+, this happens twice. You get this precipitate forming, so that's solid, and you make 2H2O. And we've got a table that we draw to record this, and I'll show you that in a minute. But it's not just hydroxides that can do this, you can also have ammonias doing the same thing. Alright, well if they're doing the same thing, you'll make the same product. So you'll make Fe, H2O4, and there'll be an OH there, water, 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 water. But in this case, you'll make 2 NH4 pluses. The point is that if you had ammonia or hydroxide, you make the same thing. Alright? So how do we record that on a table of results? And this is the key to doing well on this topic. It's realizing that the same thing is happening when we add hydroxide and when we add, what's it called? Ammonia. So, I've got a sheet of paper here. I'm going to draw it out again. This is for those of you who've watched the first video. If you haven't, well, you don't know what's going on here, do you? Here's a little revision grid. Copper, Cu2+, Cu, Fe, Al. 3+, 3+, 2+, 2+. You draw a grid. And we said, what happens when you react with OH minus? What happens when you react with excess OH minus? What happens when you react with ammonia? What happens when you react with excess ammonia? And then finally, what happens when you react with the weakest base of these 3, carbonate? Okay, so we've just said that whether you add hydroxide or ammonia, these 2 columns, the same thing is made. Watch, Cu H2O4 OH2. It's not got a charge, it's going to be a precipitate. You make exactly the same chemical here, H2O4 OH2. If you do this, Fe H2O4 OH2, I'm already bored of doing this, but it doesn't matter, you see in the point, it's the same thing, OH2. If you make this, you make Fe H2O3 OH3. It goes to the point in which there's overall no charge. If you remove 3 H pluses, you'll make this, a precipitate. You make the same precipitate here, H2O3 OH3. Down here, aluminium, you've guessed it, H2O3 OH3. Aluminium, H2O3 OH3. Same. The OH minus in here will make some water, so you'll make 2H2O, 2H2O, you'll make 3H2O, you'll make 3H2O, you'll make 2NH4 plus, you'll make 2NH4 plus, you'll make 3NH4 plus, you'll make 3NH4 plus. Alright, what about this column then? Well, hello. Copper, iron, and iron 3+, do not react with excess OH minus, only aluminium does. And we discussed this in the first video. Aluminium is so acidic, it is so charge dense, this metal ion, that it weakens the OH bond so much in the water ligands that you can eventually make aluminium OH 6 times 3 minus. We're going to do all the colours in a minute. Equally with excess ammonia, it's not a strong enough base to do the same thing that excess OH minus did, but it is a ligand. Ammonia can act as a ligand. So what you get here, if you add it to copper in enough volume, or a high enough concentration, sorry, you make CuNH3 H2O, still gone over this box, twice, 2+, and that is a complex, and it's a charged complex with 4 ammonias and 2 water ligands. And you kick out the waters and you kick out any hydroxides or whatever that might be. This is where we got to on the first video. Alright, so remember that this column and this column are the same, and they show acid-base reactions. The acids, the weak acids, and the bases along the top. Acid-base reaction. Removal of hydrogen ions by bases. Alright, I don't know what those hands gestures were. Okay, so, and then you have this one. This is another acid-base reaction, but only happens in aluminium. Aluminium is the most acidic acid, so it can lose more H pluses. And then you have this standalone box up here, which shows ligand exchange. All right, ammonias, eventually, if you put enough ammonias in, you get a ligand exchange reaction. We'll write equations in a minute. All right, colours. First, easiest one, everything in iron 2+ is green. Green, 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 green. I know we haven't done that end column, but everything is green. If it's got a charge, it's a solution. So that's a green solution. If it hasn't got a charge, it's a precipitate. Green precipitate, green precipitate. We'll come to that one in a minute. Copper, blue solution. Blue precipitate. This one, blue precipitate. Of course it is. And my ding dong, don't know what's going on there. Because these are the same thing. This is a deep blue, and it's got a 2+ charge, so it's a solution. Iron 3+, orange solution, charged solution, then it becomes a brown precipitate. And you know this column's the same as this column, so that's the same brown precipitate. Aluminium's cool, I like this one. Solution, colourless, because it's not a transition metal. Colourless solution. Brown, white precipitate, which then dissolves if you keep adding OH- to make a colourless solution. And then this is the same white precipitate as is in this column. Same. They're the same, regardless of whether you add hydroxide or ammonia, because they're both bases. All right then, we're now going to talk about what happens when you add carbonate, and I'm going to do this pretty quickly. Carbonate is a weak base, all right? It's a weak base, so it only reacts if... so you might be aware, or hopefully you're aware, because you're A-level chemists, that carbonate fizzes if you put it in strong enough acids. It gives off carbon dioxide. Well, copper and iron 2+ are not strong enough acids to cause this fizzing. No carbon dioxide is released. All you get is this. The copper ions join with the carbonate ions and you make copper carbonate. It's a solid. All right. And it's literally just the copper dumps all of its water ligands and just joins to the carbonate directly. You get the same thing with iron carbonate. Iron carbonate, green solid. Copper carbonate, well, copper's all like blues and stuff, but actually copper carbonate is a blue-green solid. Blue-green solid. So the top goes blue, 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 deep blue, blue-green. Iron 2+, green. Iron 3+, orange, brown, brown. Now what you get in this final column, the carbonate reacts with the acids in an acid-base reaction. So you get exactly the same product as you got here and here. You get Fe, H2O3, OH3, because you get an acid-base reaction just like you did with ammonia and hydroxide. You get some byproducts of carbon dioxide and you make some water. And I'll just warn you now, this is a tricky-ish equation to balance. So we're going to be writing equations in a minute. The bottom one, aluminium, it's an acid-base reaction. So you get this column, and this column, Al, H2O3, OH3, and as we all know, no charge, white precipitate. You're going to make carbon dioxide, the carbonate will fizz, and you're going to make water. So let me just say, everything in this column is the same as everything in this column, and these two here are the same as well. That is the same as that, is the same as that. You need to know special cases for the 2 pluses with carbonates. You need to know a special case for this box, and you need to know a special case for this box. But everything else on that diagram is react the same way for hydroxide and ammonia. All right. 2 plus ions react the same for hydroxide and ammonia. 3 plus ions react the same for hydroxide, ammonia, and carbonate. Excess hydroxide only affects aluminium. Excess ammonia only affects copper. And here's your copper carbonate and your iron carbonate. You got to know your colours. So colours, let's go again. Blue. Blue precipitate, blue precipitate. Deep blue solution, blue-green precipitate. Iron 2 plus. Green, green precipitate, green precipitate. You just write green. If it's got a charge, you write solution. If it hasn't, you write precipitate. Iron 3 plus, orange, brown, brown, brown. Those three are the same. Iron 3 plus is the easiest thing to remember because it only forms FeH2O3 OH3. It forms this brown precipitate regardless of the base that you use. You get a bit of fizzing over here because you've used the carbonate. Aluminium, almost identical to iron 3 plus, but it does this special thing in excess hydroxide because aluminium is very charge dense. And breathe, Norman, and breathe. We're on an inset day today in science, and we've got 1 billion jobs to do. Literally 1 billion, I never exaggerate. And making these videos for my year 13s is the priority today because they're missing loads of lessons. Hello, if you're watching this video from one of my year 13 classes. All right, let's have a little look then at how we can use this. I'm going to try now to write some equations. So if somebody says to you in the exam, write an equation, what happens when iron 3 plus reacts with hydroxide? Okay, iron 3 plus reacts with hydroxide. So iron 3 plus, you go to this box. Well, I know that is FeH2O6 3 plus, and it reacts with hydroxide. So there's the hydroxide up there. I know it's going to react with 3 hydroxides. All right, I know it's going to make just the iron 3 hydroxide, H2O3 OH3. And the 3 hydroxides will become 3 waters. Boom, easy. They then ask for observations. We know this is an orange charged solution, and we know this is a brown precipitate. So they might ask for state symbols. You'd write S there, and you'd write aqueous there. All right. If they then asked what happens when you add iron 3 plus to ammonia, well, it's basically the same reaction, but instead of 3 OH minuses, you would write 3 NH3s, and instead of forming 3 H2Os, you would form 3 NH4 pluses. Observations, orange solution, brown precipitate, because I'm going to say it again, that's the same as that. All right, what does they say in Liverpool? That's the same as that. All right, so very easy, hopefully. Next one then, let's have a look at some of these trickier versions. What happens if they ask you to say, and this is quite a common one, they go, what happens if you've got some aluminium 3 plus and you add a bit of hydroxide and then you add more hydroxide? They often say describe what happens when you add OH minus drop-wise until it's in excess. So we're going to go from here to here and then from here to here. All right, so I'm going to write from here to here. First one, aluminium H2O 6 times 3 plus. We know that's going to react with 3 OH minuses, and that will form Al H2O 3 OH3. This is going to be my white precipitate, and you're going to make 3 H2Os. I'm now here. I'm in this box, a white precipitate, a neutral, uncharged solution. Now what happens is if I keep adding it, I'm going to turn this into this. So you can write your starting point, AlH2O3 OH3, this white precipitate, and I know I'm going to end up at AlOH6 3 minus. And to do this, I'm going to need 3 more OH minuses, and I'm going to make 3 more H2Os. Square brackets around anything ionic. All right, observations. Colourless solution, white precipitate. The white precipitate dissolves to form another colourless solution. Next. Alright, so what about the other sneaky little area it could ask you to? It could ask you to write an equation that what happens when you've got copper, Cu, H2O 6 times 2 plus, and you add some ammonia. Well, if you add 2 ammonias, that will take you to this box. You will make Cu, H2O 4, OH2. That's a blue precipitate, this one up here. You'll make 2NH4 plus. And then what happens if you keep adding it? Well, if you keep adding it, you're going to end up at this deep blue solution. So that deep blue solution is Cu, what is it here? NH3 4 times, H2O twice, that's going to be 2 plus. And it's going to go from Cu, H2O 4 OH twice, so I've just written what's in that box. I'm going to then see what's the difference between this and this. Well, if you look, I've got 4 ammonias that have gone in, so I need to write plus 4 ammonias. These 4 ammonias have gone in, there they are. I've now got 2 water ligands still in there, so I must have kicked out 2 hydroxides and 2 water ligands, plus 2 OH minus and 2 H2O. Practice that one. Practice the funny boxes. Practice that one. Practice that one. Alright, makes sense, doesn't it? Practice the ones that are weird, because the examiner will ask you about those boxes. They'll ask you, everyone will know this. Most people will know this. Hardly anyone will know that. Hardly anyone will know that. That's what you need to be looking at. Final ones then. How do you write an equation for this box? Well, if you've got copper, Cu H2O 6 times 2 plus, and you add carbonate, let's just add some carbonate. Well, I know that I'm going to make copper carbonate, so that's CuCO3. That's the copper and the carbonate going together, so 6 waters must have been given out, plus 6 H2O. That's a piece of cake, that one. So these equations are easy. These ones down here just require a practice. So if you've got aluminium, Al H2O 6 times 3 plus, I know that if I add carbonate, so I'm in this box now, I'm going to make that aluminium that you make in all of the times you add aluminium, AlH2O3 OH3, that white precipitate. I know I'm also going to make a fizz, the carbonate, and I know I'm also going to make water. So I've now got to balance this equation. This one, just do it a couple of times and you'll know what to do. It's quite tricky to balance. So here's my top tip when balancing this, so you don't get yourself in a knot. If you notice here that none of the products are charged, but on this side, some of the products are charged, and I've got 3 plus and 2 minus. What that means to me is I need to make these charges balance, and then I've got a chance of balancing the equation. Whether or not you follow that, this is what you do. I've got 3 plus and 2 minus, so if I put a 3 there and a 2 there, I've now got 6 plus and 6 minus. I've now made this side electronically neutral. So from there, this should work. I've got 2 aluminiums on the left, 2 aluminiums on the right, 3 carbon, 3 CO3 2 minuses. That'll make 3 carbon dioxides. And then you can balance the waters. I'm pretty sure it's 3. Let me just check. 12, 24 on this side, 24 hydrogens on that side, 6, 7, 8, 9, 18 there. Yeah, I need 6 more there. 24 hydrogens on this side. Boom, boom. I can do it. You need to practice it. All right, I'm quite good at chemistry. You need to practice it, then you can get good too. Life goals. Be like me. Only joking. Don't be like me. Right then. So there we go. I think I've covered everything on there, but I've covered it really, really fast. I've got some chemicals out. Should I just do some of it? All right. Let's have a look. Let's take some iron 2 plus. Oh no, I'm going to go iron 3 plus. There's some iron 3 plus here. Iron 3 plus, an orange solution. No, that doesn't look right. That looks a bit too brown to me. I'm going to get a fresh one. All right. That's what an orange solution looks like of iron 3 plus. Let's just add a little bit of hydroxide. So if I add hydroxide, I should make a brown precipitate. Yay! All right, let's do it again. But this time I'm going to add ammonia. Let's see if I get, so there's my orange solution. Now we're going to slide it across to here. Let's add ammonia solutions. Get a different bottle. Ammonia. Brown solution. Same brown solution I made before, innit? And if I keep adding it, nothing will happen. It'll just stay brown. In other words, there's no room that way, there's no room that way. It's stuck in that column. I haven't got any carbonate out with me, so you're just going to have to trust me on that one, that you make the same brown solution here. I can't make any of them. I'll show you the copper one again, because it's my fave. Because, you know, I do actually like chemistry. Have I got any ammonia left? Got a little bit of ammonia left. So I'm going to put a little drop of copper in there. Alright, so that's where I am now. Got some ammonium hydroxide, a little bit of ammonia, nearly used it all a minute ago. So I should, if I add this, I should make a blue precipitate, and then if I keep adding it, it should go deep blue solution. I might not have enough, so let's go. Ooh, do I get a blue precipitate? Yeah, there it is. Can you see the deep blue already occurring around the outside? I'm not going to have enough. I might have enough. I've got a bit of a mix between them two. I'm probably about there. So I can get another few drops in. I'm out of ammonia. Oh, I might have another bottle. Got another bottle. You should see this desk, it's so messy. Swirly, whirly, 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 whirly. I'm there. Ligand exchange. Ligand exchange reaction. You need to practice that equation. Oh, chemistry's easy. Watch this video a couple of times, hopefully you'll agree. Got one more little bit to do. Okay, so how does this become useful? When does this become useful? Alright, so this is when it becomes useful. Because you do this. You're in your exam and you're stuck and you can't quite remember, and you go Q, Fe, Al. 3 plus, 3 plus. You know, in the exam, hopefully you remembered some stuff, so you're not doing it from scratch. What do I remember? OH, excess OH, NH3, excess NH3, carbonate CO3 2 minus, okay. Those two are different to each other. That is, for example, CuCO3, FeCO3. I know them. If they say, what does excess OH minus do with copper? You go, haha, you're not catching me out because nothing happens. You know that that's the only one that excess OH minus what matters with. Excess ammonia. With excess ammonia, there's your ligand exchange one that you need to practice. Here are the two equations that you need to practice balancing, because they also make CO2 and H2O, CO2 and H2O, so they're a little bit trickier to balance. If you know this chemical, you know this chemical and this chemical. If you know this one, you know this one, you know this one. If you know this one, you know this one. If you know this one, you know this one. They are acid-base reactions because these are all weak acids. In video 1, I told you why. The metal ion pulls electron density towards itself. Sorry, the positive metal ion pulls electron density towards itself, which weakens the OH bonds in the ligands, so the H plus ions are released into solution. This is the strongest base, so it does something extra special to the strongest acid. This is slightly weaker base, so it just makes the hydroxides. This is the weakest base of the three, so it only reacts with the strongest acids in an acid-base reaction. My classes, I'm going to send you some questions on these that I'll need you to do. You don't really have an option on that, I'm afraid. You just got to know this for your A-levels. This little diagram here is quite useful. If you manage to sit through both of those lessons, well done, you're probably going to get an A-star. If you gave up halfway through, well, you're probably not hearing me saying this. So if they gave up halfway through, they're going to suck. You're going to do loads better than them. Well done for making it to the end. Thumbs up. Bye.